Welcome. Today we're talking about modeling data with two variables. So throughout chapter 3, we're going to be working with two variables at a time. So while we do this, it's really important to pay attention to which one's the x variable, which one's the y variable. So here's an example, a real life example, where we have a graph. So let's read what it says down here. It says figure 1, it's the share of all income held by the top 1% in the United States from 1990 to 2013. And then there's a source. Good, they didn't plagiarize. You always got to put your sources there. And there's dots here, but then there's this line. So this is called a trend line. So what we're doing in chapter 3 is talking about straight lines and their equations and how to graph them. So one way that straight lines get used a whole lot is with real life data and trying to find what the trend is. And that's what this is depicting. One thing to recognize here is that the x variable is the year and the y variable is the percentage. So remember, x is always on the horizontal axis, y is always on the vertical axis. And so that's always important for us to look at and to notice like what's x and what's y. So let's see what they're asking us for. So state the data values for the years 2000 and 2001. Data values, in this case, since there's two variables, should be points. So we want to know in the year 2000, what's y? Because x is the year, so we're looking for y. And then in the year 2001, what's the y? So let's go up to our table. And in the homework, I know sometimes it's hard to see graphs or to read them really closely. I think the homework also gives you a table of values, so you can always go there if the graph isn't as legible as you'd like it. So here's 2000 on the x. I'm just gonna go up to y, and I'm not stopping at the line, I'm stopping at the actual data point. And it looks like if I follow that value over here, that's at 22. So in this case, that's 22% of all income is held by the top 1% in the US. So we're looking at how, the rich get richer, so to speak. So 22% of all the income was held by 1% of the people. So I'm putting 22 down for y. Let's do the same thing for 2001. So I take 2001, I go up to the point, and then try to find what the y value is. And it looks like it's at 18. So at 2001, the y value is 18. Then it said, how did the percent change in this year? So what we're going to be talking about in section 3.3 are rates of change. So in a rate of change is usually a subtraction. We want to know what's the difference between those two. So we're going to take 22 minus 18, and that would be 4. But for rates of change, and especially for any word problem, we need to label units. So that's percent per year. In a rate of change, we're always going to really have 2 units. And another way to put this, let's just say, is with a divided by. So if you wanted to abbreviate it, you could be percent per year like that. But with a rate of change, we'll have 2 different units. And we'll see that throughout this section, but I just want to make that out there now. That we're really talking about both the y and the x units at the same time when we talk about how we change. All right, let's do another one. 2002 and 2007. So we're going to start with points. 2002, comma, we got to find the y value. 2007, comma, got to find the y value. So let's go in the graph. So in 2002, I'm over here. I go up to this point, and it looks like the y value is 17. In 2007, so that's 2 past 2005, I go up, and make sure you're hitting the point, not the trend line. And up at the point, it's 24. So that line doesn't perfectly predict what actually happens. We want to go to the actual data point. Or again, the value in the table on some of the homework too. All right, then it says, how did the percentage change over these 5 years? Okay, well, we'd take 24 minus 17, and that would be 7. But now, this is percent over 5 years. Right? It's not per year anymore. We're talking about over 5 years. So really what this is 7% divided by 5 years. And that we're going to need a calculator for. So I'm just going to do 7 divided by 5 equals 1.4% per year. So again, rates of change have both an X component and a Y component. So the percents are Y's, the years are X's. And so it's always a comparison between how Y changed and how X changed. And then we divide. So another way to say this is that a rate of change is the change in Y divided by the change in X. And that's really what we just did, right? We subtracted to figure out how much the percentage changed. And I got the over 5 years by subtracting the X's. So we're going to end up subtracting the Y's and subtracting the X's. One way that this is written mathematically is with a triangle. So I want you to at least have been exposed to this notation because we might see it. This triangle is actually a capital delta in the Greek alphabet. So I don't know where you may have seen that before, maybe with fraternities or sororities if you know anyone who's in one of those. But in mathematics, that always means the change in. Because mathematicians love to measure how something has changed, and so that triangle means that. Okay, let's turn the page and see some examples that aren't graphs. I'm gonna get this one out of here. All right, so this is patterns in tables. So again, we're looking at X and Y in relationship to each other. So we want to know, how could Y be calculated if we know the X value? So our equation needs to be Y equals something. And then we'll find the rate of change if it's a constant rate of change. What that means is if it's actually a line, linear. So let's try it out. So in part A, what I'm going to do when I look at these patterns and tables is, well, first you can just check to see if you see a relationship between the X's and the Y's, right? Like, so how do you get from 3 to 12 or 2 to 8 or 1 to 4? And so some of us may have already seen like, oh, you just multiply by 4. So if you already noticed that all this is that you multiply by 4, well, that's the equation Y equals 4 times X. So how we got from X to Y is to multiply by 4. So the equation we write is Y equals 4 times the X value. Awesome. So the rate of change, to find rate of change though, we always look for what's the difference in the Y values. Remember, rate of change is that difference in the Y values over the difference in the X values. And sometimes it's hard with negatives, so you can skip down to where it's positive if you want. From 0 to 4, the Y value changed to 4. 4 to 8, the Y value changed 4. 8 to 12, the Y value changed 4. So that's what the directions meant of the constant rate of change. So our rate of change here is 4. But we also want to make sure that at the same time the X is only increased by 1. Right? Because sometimes some tables might have the X's go up by 2s or 3s or something else. So we always look for how does the Y change over how do the X's change. So from here to here, the Y's went up 4 while the X's went up 1. So our rate of change is 4. All right, let's try it again. Now, so one thing to do is to see right away if you see a pattern. It's like from 1 to 5. Maybe it's multiplied by 5. It could be add 4, 2 to 9. You can't multiply and do that. So this is now a little tricky. So let's start with the rate of change, actually. Let's see if that's constant. And again, I like to skip to positives. 1 to 5, it increased by 4. 5 to 9, it increased by 4. 9 to 13, increased by 4. So it looks like the rate of change is that the y's increased by 4, while the x's went up 1. Remember, it's always that comparison to how the y's go up versus how the x's go up. So this rate of change is again 4. So looking back at the previous problem, we might think, oh, well, then the equation should be y equals 4x, and we'd be very close. We just need to add or subtract something. So now that we know the rate of change is 4, let's see if we can figure it out. So if I multiplied 1 times 4, I'd get 4. And then I need to add 1 to make 5. All right, so if we're getting this, I'd need to multiply by 4 and then add 1. Let's see if that works for the next one. So 2, and again, I got the 4 because that's the rate of change. 2 times 4 is 8. Oh, and then I need to add 1 to get 9. So it looks like this is a pattern. We always want to try it out a third time just to make sure. 3 times 4 is 12. Then if I add 1, I'd get 13. So I think all we need to adjust this is 4x plus 1. So the rate of change to help us find that 4x, but then we had to sort of play around with it to figure out that plus 1. You had to do some problem solving with these. All right, let's try the next one. So we look, -2, how do you get it to 4? Ooh, and this one's different because it went negative to positive. And this one's positive to positive. Maybe 3 and 9 is a good clue. So, because the problem is you just sort of have to see it. That I know that 3 squared is 9. That's one way to get from 3 to 9. And 2 squared is 4. And 1 squared is 1. And 0 squared is 0. But does this work for the negatives? Let's see. -1 squared. Oh yeah, that's positive 1. Because when you square a negative, it becomes positive. So yeah, this totally works. So now we just have to write it as an equation. And that would be y equals x squared. Now, rate of change, if we started subtracting, we'd get, well, this is, again, I like to skip ahead. This is like 3, this is 5. It's not constant, it changes. So we can just say that this is not linear, meaning it's not a straight line. Anytime you square an x value, that's not going to be the equation of a line. It actually makes a parabola, if that's something you've seen in a previous class. If not, Math 65, we talk a lot about parabolas. While I'm here, I want to mention, maybe give you a hint for the homework, that in the homework, you might see something a little similar to this where positives become positives and negatives become positive. In the homework, you might see like a y equals absolute value of x. That's another kind of formula that turns negatives to positives. And the opposite of squaring is a square root. So the way to type square root is SQRT. So that's the same as square root of x. But that's how you type it in WebWork. So a little homework hint there. Well, let's try another one. Those are 2 other functions that are not linear. So that's the reason I was thinking of them. Absolute values are sort of fun equations because they make v's instead of u's like parabolas. And square roots just sort of do this. It's like a half parabola on its side. You don't need to know the graphs, but we'll be looking for these kind of patterns in the homework. All right, let's do another one that's linear, hopefully. So one big difference in this table is that the x's are going up by more than 1 at a time. But we still need to find an equation. So again, I like positives. How can I get from 100 to 10? Or 200 to 20? Do you see how it's just taking off a 0? One way to take off a 0 is either that you can divide by 10, but dividing by 10 is the same. Well, let's actually write the equation, because let's do that first. It seems like the pattern is whatever x is, we have to divide it by 10. So I'm going to write y equals x divided by 10. When you write divided by in algebra, you should not be using this old school division symbol. Fraction bars every time. All right, so we got this, but the rate of change, we need to look at how y is changing and then look at how x is changing. So the y's, I'm going to start with these positive ones. 0 to 10, it went up by 10. 10 to 20 went up by 10. 20 to 30 went up by 10. So the y's are going up by 10, but the x's, 0 to 100, the x's are going up by 100 at a time. So it's going to be 10 over 100, which reduces to 1/10 as the rate of change. And it's sort of in that equation as well. All right, let's look at these, because what this rate of change is actually something called slope. The slope of a line is how steep or flat a line is. So we're gonna, on the next page, look at some different pictures and see if we can recognize some slopes. Here we go. Slope is this rate of change. And one thing, when we're finding slope, remember we're looking at how y is changing over how x is changing. So we almost always need a triangle. Let me draw. That was a weak triangle. This is why I told y'all you need a straight edge for this chapter, and then I didn't do it. So please use straight edges when drawing lines. All right. So, and I'm gonna make a different kind of triangle too over here. All right. So a lot of times when we talk about slope, we're looking at this diagonal and how flat it is or steep it is, whether it's going downward. Like, so if Amy's walking on this triangle this way, I'm going downhill. And I always walk left to right. Just that's how we read graphs in math. And then if I'm trying to walk up that's full on mountain climbing at that point. That's really steep. So it's uphill, which means that it's going to be a positive slope versus a negative slope. So we can talk about how steep it is, but also whether it's positive or negative. But in order to measure that diagonal and how steep it is, we need the x and the y. So remember, we're always looking for how does y change and how does x change. So we need to be able to make that triangle in order to measure it. Another way we may have heard slope is rise over run. That means the exact same thing as how does the y change over how does the x change. So let's look at these. We're just going to look for signs where we can make one of those triangles. So this first one, the steepness of roads are measured with percentages. And these are especially important for people driving trucks, right? That those of us in cars, sometimes it does make a difference, but it really makes a difference if you're trying to haul a really heavy load and all of a sudden it goes uphill or downhill even. You have to be really careful about that. So right away I can see, oh yeah, I can make a triangle out of this. So that's slope, yes. That's a rate of change that they're talking about. I love otters, y'all, but they don't have anything to do with rate of change. Nope. This is a downhill, right? That at least the way that truck's going, they have to be really careful about like going down too fast if they're carrying something really heavy. So yeah, that's definitely a slope. This sign means that when it gets really cold, it gets icy. That's not rate of change though. It's an important sign to know about, that it's icy conditions are possible, but no. Falling rocks, again, important sign, not a rate of change. Another time that slope is really important is for people who use wheelchairs, that wheelchair ramps have to adhere to very specific guidelines so that everyone's able to use them. So yes, that is definitely a slope. And do you see how it makes that triangle? That's what we're looking for. So we're talking about the steepness of the diagonal, but we measure the steepness by measuring the y and the x. Bike riders, again, that can really change how they're riding. If it goes really fast downhill, they need to be really careful. A ratio is another way to measure a slope. But for us, we're just looking at that triangle. But what that 1 to 5 means is that the change in y is 1 and the change in x is 5. So the slope is 1/5. So that sign actually puts it in terms of slope like what we're going to be talking about. And then this is what I would consider non-linear. Remember, we talked about how things like parabolas and square roots and absolute value and lots of other kinds of curves don't have slope because they aren't a straight line.